In the domain of communicable diseases, a pandemic is a worst case scenario where the whole world is currently going through. Contact tracing has been a major technique to control the spread of disease. Typical contact tracing is conducted in a manual strategy which is inefficient and extremely time consuming. This really relies on manpower and is not scalable as well. So, to overcome these, different kinds of digital tools have been introduced around the world. Digital contact tracing is more efficient and easier than the traditional way of contact tracing. Even though using technology is more efficient for the problem, it should be compatible with any circumstances and should be applicable to anyone. But most of the contact tracing tools that have been invented fails to get this certain approach. Thus, most of the tools have been introduced are smartphone applications, which the solution will be limited to the smart device users. So, a considerable amount of set of individuals will be eliminated from the solution. School students, kids who are not grown up to use smartphones, elderly people who don't know how to operate a smartphone, individuals who cannot use mobile phones due to other reasons like blindness, or people who are with other disabilities, and people who are not affordable to buy smartphones and lacks in technical knowledge are most of the individuals who will miss out from the solution which have been introduced around the world. So, we have come up with a solution where contact tracing is done without the use of smartphone application, and the tracing process could be carried out for those missed out groups as well.
We are Team Simple Tech. I am Kavin Punikraman. Current contact tracing application architecture. There are three types of application in now. They are centralized architecture, decentralized architecture, hybrid architecture. Centralized architecture. When a user is self-registered via the application, it communicates with the server and a temporary key is generated and sent back to the application. The temporary key is encrypted with the secret key and stored in the server, which is known by the server only. The temporary key is backlisted and changed every 15 minutes. When the user is in close contact with another individual who has installed the application, the temporary IDs are exchanged via Bluetooth encounter messages. When a user is tested positive, he or she can manually release their respective contact information. Then using the temporary ID receive the servers map it with the secret key and alerts the users who have been in contact with the individual who has been tested positive. Decentralized architecture. Unlike the centralized architecture, the decentralized architecture does all heavy lifting in the mobile application itself. This is done to enhance the user's privacy. This methodology does not include the registration phase. As soon as the user installs the application, a seed, something similar to unique ID, is generated, and this seed changes every hour. Every minute, this seed along with the current timestamp combined together and encrypted to the generate what is called stream. This unique stream is what is used to expose the users to the public environment. Whenever user is in close range with another user who has installed the application, these seeds are broadcast via the Bluetooth beacons. When a user is tested positive, he or she can manually upload their seeds information to the server. Normally, user can download the update seeds on a daily basis, and the application checks locally whether any of the seeds match the locally collected seed data. This type of collection, transmission, and retrieval process does lead to any form of data links attacks. Hybrid architecture. The hybrid architecture incorporates both methodologies to perform contact tracing. When a user is registered and authenticated, the server generates unique ID and a secret and send it to the application. As soon as application receives data, it is deleted from the server. Advantages of the centralized architecture. It is a lightweight application and the server does the heavy lifting and perform the risk analysis. Disadvantages of central architecture is the server has user information. In case of an attack, all of its data and contact data will be stolen. Let's discuss about the existing gaps in current contact tracing, data collection, storage and transfer. First one is device verification. The biggest drawback of the above mentioned architectures were that since it was a mobile-based solution, hacker can get in between the process of passing contact information to the server and pass in invalid contact information, which can lead to invalid contact maps. Second one is contact tracing for everyone. Above architecture solutions are totally based on mobile phone solution. The main issue with the mobile phone is that not anyone and everyone has access to the mobile phone, which has access to the internet in the third world countries like Sri Lanka, India, Pakistan and Nepal. In conclusion, the main two gaps of the lack of the research in area like actual device verification and the availability of the solution to a more mass audience, where infected contact can be identified in a short time span and quarantined or even isolated depending on the severity of the case.
So I will be explaining about the architecture of how we were able to design the proposed solution. And as per the research gap, we had to prepare our own device because the research gap was on that most of the solutions use a mobile device, and there are major industries that do not have the access or do not let their employees use their mobile phones during their work hours. So we have created our own Tracemetric IoT device, which is powered by Node MCU. And basically, what this device is, what we have planned to do is we will give these devices to every single member of an organization. And when two devices get in close range with each other, it detects a contact and it reports to the Tracemetric servers. So the biggest concern that we had while preparing this solution is data privacy. Having contact data and storing them in the most safest possible way is very important in a solution like this. So what we decided to do was we will be only storing the user's contact related data in the Neo4j GraphDB. So why we have chosen Neo4j is because we don't have to make structures like what we do in SQL, and it's not a relational database. We can easily make different nodes and correlate them with relationship, and it's much faster than any other database for our use case. So we thought of using Neo4j, and then we thought, okay, where do we fetch the user related data? So we will be giving the option for the organization, and we will be providing them with the UI dashboard. We'll be giving them the option to provide a connection of their own. So for now, we support MongoDB. We have developed the solution in MongoDB. We have used the online Atlas cluster. So during login, the user can provide the connection details such as host, port name, username, password, and we will be giving them a specific username for their organization, and they can simply log in. When they log in, what happens is the dashboard calls the Tracemetric middleware, and the middleware is the component that contacts the organizational DB and Neo4j DB. So any sort of mapping happens in the middleware. So the data in this format, when we do it in this format, the data is divided in two different places. And then so simply when the login calls or the device details calls or user details calls, everything goes to the middleware, and according to the type of the call, it is routed to either MongoDB or Neo4j. Dependent, sometimes it's routed to both, and data is taken to the middleware and mapped. And then next flow is how do we get the contacts into our system. So what happens is the IoT device basically sends a simple call with a message, a post message. So the IoT device also maintains a contact queue, and it offloads time to time. When it has an active internet connection, it offloads from time to time. So what the IoT device does is it contacts the middleware, and the middleware does a post request that we have made via AWS. It uses the AWS gateway with authentication, and it goes to a queue. So why we chose a specific queue was, during our tunes when we were discussing, we thought that if there are 1,000 devices, and if there are 1,000 people at the same place, there's going to be millions of contact points that will be coming in, and we cannot lose any contact. So we thought we have to use some sort of a queue messaging streaming system. So we went over Kafka and all of those things, but since we were using AWS, we thought we can use simple queue system AWS SQS, because it's easily integratable to Lambda and all of the other internal services. So we used SQS. So simply what happens is, when the call comes from the IoT device to the middleware, it goes to the through the gateway, it goes to the queue, and the queue works in a first in first out method. So first message in, it will do whatever we instruct the queue. So in this case, we have put a lambda function as a trigger for the queue. So what this lambda function does is, it simply verifies whether this device that is sending data is our own device, or either whether it's another foreign party. It will simply verify that and send it to the Neo4j GraphDB. It'll just keep on making connections in the Neo4j GraphDB. And the UI dashboard keeps fetching this data. Then next, when we go for our data science component, we needed data science component is basically an insights dashboard that we have given the organization. The insights dashboard contains of many useful insights for the organization. For an example, how many days will it take for it to recover a machine learning model is running there, or how many users are there in the system, how many devices are there in the system, and what are the days, like in a pie chart, what are the days where there are more contacts. So what simply happens is, it also calls the API gateway, and the gateway makes the connection to Lambda, and Lambda calls Neo4j and returns insights via an API to the UI dashboard. So this is the entire architecture for the Tracemetric system.
I'm going to briefly explain the core code and the structure of the Tracemetric front-end application. So here what you can see is the root directory, and we have structured the application as components, config, containers, environments, pages, services, and the store. So components basically contains the basic components of the application, such as a footer, header, and sidebar. So the config directory contains the router.js file, which defines all the routes of the application. You can add or remove pages, and it will be reflected on both menu and the routings also. So we have dashboard page, device registration page, ranking page, along with their routes. So containers include the containers of the application. So here we have the dashboard container, which is the main layout of the application of the dashboard. So it has a sidebar, header, content, breadcrumb, and the footer. The environment directory, we have added two environment configurations, which are developed and the production. This pages directory, these are all the pages which will be displaying throughout the application, which are dashboard, device registration, organization, ranking, and settings page. In this dashboard page, you have some widgets which will be displaying to the user. Implemented some graphs, charts, stat cards, tips in this component. The services directory contains all the services of the application, including REST API integrations. Here we have auth service, device registration service. So we have used Axios in order to communicate with API endpoints. So the store directory basically contains Redux, actions, and reducers. to maintain the status of the application. So here we have auth action, device registration action, organization action, auth reducer, device registration reducer. We have used Redux persist to maintain the auth state of the application inside the local storage. I will explain the user interfaces by walking through the front-end application. I'm going to walk through the Tracemetric front-end application. So here is the login page of the application. So here the organization should provide a own database instance in order to log into the system successfully. So the landing page of Tracemetric dashboard is the dashboard page. Here we have some widgets to give insights to the end user, which means organization. So the contacted days graph, you will be able to identify which days are the most contacts or interactions happen. By the help of this, the organization can make decisions to plan their work from home days. And so the infection timeline is showing the count of the members who were infected during this timeline. Will be showing all the devices which belongs to a specific organization. So it will be using to map the tracing devices of the organization with their members. Here you can add member details. So organization also be able to use this ranking feature, which will be rank members based on their infection probability. First you should select some infected people like this, and you can hit generate button. So it will be showing rankings and who should be isolated, and this is the first level contacts graph.
In the middleware component, the whole middleware component was written using Node.js. When it comes to the core code, let me explain briefly about the APIs and the calls they make within the code. So I used express route functions in order to call the HTTP methods. The login API calls to the Neo4j database and checks for the user, and also if a user is not found, it pops up an error, and if a user is found, it checks for the relationship password. It checks for the password of the relevant user, and if it is if the given password is correct, the user is logged in, and a token is generated along with the response body. And if the password is incorrect, the response unauthorized is generated. Let me explain briefly about the device detail API. So when it comes to the device details API, the device details are taken using the MongoDB's two collections, that is member device and member collections, and the queries are executed. Find queries are executed to get the details and stored in arrays, and each item is processed and checked for the given member ID, and if the member ID of the member device and the member collection are equal, then the user is checked for the mapping end date, and if the mapping end date is null, the device status is given as active, and else it is given as inactive and passed along with the response body. So that is the device detail API. Let me explain briefly about the ranking generation API as well. So basically, the ranking generation API calls for the Neo4j database and checks for the user once the device ID is passed along with the request body. So if a user is registered to a certain device, the property is infected is set for true, and the reported timestamp is taken as an epoch, and the user is returned. So if the user is not, if the relationship is null, the response is given as not registered user. And if there's a relationship between the user and the device, the else the else code is executed, and within the else, this function is executed to get the insights from the Lambda endpoint, AWS Lambda get insights endpoint. So once I get these insights, I use those insights to check with the database, MongoDB that is, to check with the database and get the user's relevant details. That is the first level contact details, and stored in separate JSON, and passed along with the response as well. So the parent user's details are also taken from a DB call, and they are also passed along with the response item. So it should be noted that the ranking here is based on age. So once the isolation data is taken, the item is the relevant item is sorted using the descending order of age, that is ranking the highest aged members as high risk, and descending order, ranking the lowest with the less age than that of the first user. So the ranking is based on age, and that is the ranking details API. So overall, when it comes to these APIs, the middleware comprises of these APIs, and the relevant information and data is passed along to the front end as well. Thank you.
So I will be explaining how the Lambda functions have been set up for the Tracemetric project. So basically we have two Lambda functions. First, as we have explained in the architecture diagram, there we needed a Lambda function to communicate between the queue service and Neo4j DB, because there will be many contact entries that come through from the IoT device to the queue and from the queue to the Neo4j DB. So we wanted to clean up some of that data. For an example, we didn't want devices which were not authorized from our end to send data, which will create incorrect contacts, which will be an issue for the entire program. So that is one Lambda function that we have developed. So this Lambda function simply takes in the contact device ID and the parent device ID that is sent from the queue, and the queue gets it from the IoT device. We check whether this device ID is present in our Neo4j database, and if it is present, then we make the contact between those two devices. Yes, for this function, that's what this function does. And then next we have our insights endpoint. As you we have a UI dashboard, and our data science component is run by insights. So this insight has some data cleaning portions, and it has a machine learning component that runs behind it for one particular insight. So this Lambda function actually takes care of giving insights to the UI dashboard. We cannot see the code here. I will be explaining the code separately. All of these Lambda functions are paired up with the API gateway service that's offered by AWS to call publicly. So if you see here, this SQS proxy is used to connect to the queue to Neo4j. This proxy is used by the IoT device to connect to the queue, And next, the tracing insights proxy. This API gateway is used to connect to the tracing insights Lambda function. So whenever a request comes, it goes to the API gateway and next to the Lambda function. And as well as that, this is the graph database that we use. It's called Neo4j. And as you can see, these are all the values that have been, these are the devices. The red nodes depict devices and blue nodes depict users. So whenever a message comes to the queue triggers the Lambda function. As we can see here, we have a queue trigger set up here. It will set up, and if it passes our conditions, it will create a contact in this manner. As you can see, it will create a contact in this manner, and it will pair up the device's contacts. So that is the process for the Lambda function setup. So if we go to this insights endpoint, this is where the different types of insights that we use for the insights dashboard. This is the code which provides those insights, the code that powers the Lambda function as well. So initially what we did was we had one insight which predicts the recovery days of a certain patient dependent on their age, since we have the age data. So we basically used a data set that we found from Kaggle, and we cleaned up the data set. We dropped all the unnecessary columns and dropped the NA values. And then two things that we had to do was normalize the age, because we had age in a range format, as you can see here, 50s, 60s, 30s. So what we did, we had to split it using regex, turn it into an integer, and randomize the age values. And then we had to find the difference between the symptom onset date and the release date. That part, the code cleaning and processing part, is handled by these two functions. And then we plotted the graph to check what type of an algorithm, machine learning algorithm, that we can apply for this specific insight. So since we had two variables, one dependent and one independent, we thought of going the easy way of a simple linear regression. They have used the sklearn library and fitted the data to the linear regression, and we have checked few prediction values. And plus, after that, when we thought of deploying, we had to find a package or a library that helps us, because we cannot upload the CSV files and the model files into the Lambda function. What we have done is we have used a package called Pickle. This package helps us to dump this model into an unreadable file, and we can open this file from wherever we want. So that's what we have done in the model loader. So basically, this model loader function is what runs behind the Lambda function. So if I have to explain, the recovery period predictor, as this specific insight is what powers that UI dashboard to run for that specific UI, for that specific so this particular function is what powers that UI component, the recovery date predictor. So simply what we have done is we have called this loaded module using this non-readable age versus recovery days file, and we have passed the age of our users in our particular system, and we have predicted how many days it may get from the time of contact to recover, and we have provided that endpoint. And then if you check, there are many other insights that we have provided for the dashboard. So if I had to go through, we have the total number of users in a system in a particular organization, then the total number of devices that are there for that particular organization, and then the total attacks that are happening in that specific organization. Then we have the total infected count who have been given by the organization that they're positive for COVID-19 or whatever pandemic. Then we have our machine learning model function, the recovery dates, and then we have the contacted days. So for an example, we thought it's a good idea to give to the organization manager on what days are the most contacts occurring. So it's given in a percentage wise. I will show the response that we get. It shows the percentage failed contacts, so the organization can take a decision on how they must bring in their members. And then we have the infected months, in which months the count of people that have got infected. And then we have another insight of the idle devices that are not being used. And then we have another very important insight that we give to the users about which users are in the organization but do not have a device mapped with them. So that is another insight that we give them. Let me show the response quickly. So if you see here, our final, as I have explained, the insights endpoint, where we have deployed and got a public invoking URL from API gateway, where we can do a simple get call and get the insights that we need. So if I send this request, it does its computation, and here we go. It gives the total number of users, total devices, total contacts, and then of the contacted, first level contacted individuals, we provide which dates they're going to get recovered, and then we give, so for an example, the company can see, okay, on Friday there's 25% contacts, on Thursday there's 50% contacts. So there are certain insights given from that. And then we have infected months. We have infected months, in which month in April there were 9 positive cases, in February there was 1 positive case. And then we have another insight or another data. Some of the data that we expose via this endpoint are the first level contacts. So these are the parent users who are positive, and their first level contacts, their device ID, when they have got contacted, their user ID and age. We don't pass any user related data, since we do not have user related data on our end. We have it, the company manages it on their local data storage. So these are all the positive cases who are positive, and these are their contacts, their first level contacts. So this is basically how the response looks of our insight endpoint. And then we have, this is the post request that we used to send the parent device ID and the contact device ID from the IoT device to the queue, which then the queue triggers the Lambda function and moves to the Neo4j database. So that is the full Lambda integration and code explanation for the Tracemetric architecture.
Let me introduce our IoT device briefly. So basically our IoT device collecting, basically it's scanning whatever the Tracemetric device nearby, and it stores whatever the tracing data inside the EEPROM. And when it detects extraction point, so it will automatically upload the whatever the data to our cloud servers. The extraction point is might be a open Wi-Fi network inside the organization, or else we can place extraction points in nearby security gate, or else exit door or something like that. So basically in this code we have configurations. So the SSID means the broadcast SSID. So it means, so it should contains Tracemetric keyword in there. And also this is the device ID. So basically device ID means you can put the whatever the numeric value inside the SSID, as well as you need to input the same value inside the device ID. And this is our ESP web server. So we need to hold web server, because we need to broadcast our SSID to our other devices. I mean Tracemetric device identify other Tracemetric devices. So for that we need to create a hotspot. For that hotspot we need a ESP8266 web server, middleware code as well. So this is the middleware. So in this middleware there is a front end operation as well, but in this middleware we created the router, because this I need to mention this as well. This is created with Node and as well the Express framework. So we are using we created a router and we imported the router to the index file, and in the routes folder we have router and we have method trace submit. In this method we use trace submit.
I have contributed to the front-end component, such as for the admin login and organization management dashboard. And I have contributed to the data science component by fitting the clean data to a linear regression model. And I was able to contribute for the data visualization part as well by giving the insights on organization's idle amount of devices and the count of unregistered users. And I have contributed to the implementation report also by covering the chapter 1's implementation of the front-end component and chapter 3 evaluation.
I am Kavin Gunikrama. In Simple Text Solution, I have mainly contributed into system middleware. If I get component wise, they are device registration and device deactivation. Also, I have added plotting and decision feature in data science component. By adding testing chapter, I have contributed in documentation.
Hi, I'm Lilan from the group SimpleTech, and our implementation is the Tracemetric solution. So when it comes to the overall individual contribution, I contributed individually for the project in both the documentation and the implementation aspects. When it comes to the documentation, I contributed by writing on the aim in the initial PID, previous work in the literature review, and when it comes to the SRS, aim and research questions, methodologies, chapter overview, models, chapter summary, etc. And when it comes to the implementation, I contributed through creating middleware APIs in Node.js, and also by contributing to the data science component in the Tracemetric solution. So that's it when it comes to the overall contribution for the whole project in an individual aspect. Thank you.
I'm Sandrupal Bhugi. I have mainly worked on the front-end component of the Tracemetric. Component-wise, login, dashboard, device registration, user ranking, and the organization management features, and also contributed to the machine learning component as well. So for the data cleaning and some data calculations based on the data, I have also contributed to the data visualization component by adding several insights. If I name those, infection timeline, contacted days, and infected members, I was able to contribute to the implementation document as well by adding overview of the prototype section. So my IIT number is 2017-304.
I'm Chamikara Samarsekara. I mainly contributed to IoT device, which is collecting trace information, and also I contributed to resolve the problems in the project, like middleware problems, as well as the DB problems, and in the middleware as well. So also I did the whatever the CI/CD part in the middleware application.
Hi, my name is Darren Rumendra Gomez. I have mainly contributed towards the Lambda functions, the two Lambda functions that connects the queue and the Neo4j DB, and the Insights Lambda function. And mainly in the Insights Lambda function, I have contributed towards the machine learning model, where I clean the data and organize the recovery dates. And also I have contributed towards the CI/CD pipeline for the Lambda functions and the middleware. and as well as the React UI dashboard. And also I have written the chapters for implementation of the data science component, implementation of the CI/CD pipeline, and the very final chapter of the goals achieved, future plans, and the extra work done. So that is my contribution towards the project Tracemetric by Simple Tech.